Welcome back. In my previous lecture, I have given the statement of and the proof of the Cayley-Hamilton theorem. Now, in this lecture, I will give you the questions based on Cayley-Hamilton theorem, and then I will try to find out the inverse of a matrix using the Cayley-Hamilton theorem. Cayley-Hamilton theorem means every square matrix satisfies its characteristic equation. Now, in this lecture, I will give you the questions. So, the question number 1. So that the matrix A equal to 0, 1, 2, then 2 minus 3, 0, and then we have 1, 1 minus 1, so that this matrix satisfies its characteristic equation and evaluate, and hence you have to evaluate the value of a power 6 plus a power 5 minus a4 plus a cube minus 8 plus a cube plus 4a square minus a plus 12. So prove that this matrix satisfies its characteristic equation and evaluate the value of this matrix, and also calculate A inverse. So further we have to calculate the inverse of the matrix A. So solution, your characteristic equation is given by determinant A minus lambda I equal to 0. So from here we have minus lambda 1, 2, 2, minus 3, minus lambda 0, 1, 1, minus 1, minus lambda equal to 0. So let us solve this determinant. So we have minus lambda into minus 3 lambda, then we will have minus 1 minus lambda. Now then this is your 0, then we have minus 1, then we have minus 2 lambda plus 2, then we have 2 plus 3 plus lambda equal to 0. So this is equal to, now this is your minus minus plus, and again we have minus sign, 1 plus lambda, 3 plus lambda, then we have minus minus plus 2 lambda plus 4, this will be your 10 plus 2 lambda equal to 0. Now, if you solve this one, then we will have lambda square, so we have minus lambda cube, then we have 3 lambda plus 4 lambda, so we have minus 4 lambda square, then we have plus 3, so we have minus 3 lambda, then this is your 12 plus 2 plus 2, that means 4 lambda, so we have 4 lambda equal to 0. So from here we have lambda cube plus 4 lambda square plus 3 lambda. Now this is your minus 3 plus 4, so we have plus lambda, so this is your minus lambda, and then minus 12 equal to 0. So this is your characteristic equation. Now, so this is your lambda cube plus 4 lambda square minus lambda minus 12 equal to 0. Now we will show that the matrix A satisfies this equation. That means if you put lambda equal to A, then this matrix is equal to 0. Now, say this is equation number 1. Now we show that A satisfies equation number 2. Equation number 1, that is, we will prove that A cube plus 4A square minus a minus 12 is equal to 0. Now we will show that this is equal to 0. So for that, let us compute a square and a cube. So your a square will be equal to a, your a is 0, 1, 2, then we have 2 minus 3, 0, then we have 1, 1 minus 1. So this is your a multiplied by a. 0, 1, 2, 2 minus 3, 0, then we have 1, 1 minus 1. Now it is equal to row into column. So we have 2 plus 2, that is 4. Then again row into column, then we will have minus 3 plus 2. So this is your minus 1. Then this is your 0, then this is your 0, we have minus 2. Then row into column, so this is your 0, then we have minus 6. Then again row into column will give you plus 2 plus 9, so 11. Then this is your 4, 0, and then again 0. So we have 4. Then this is your 0, this is your 2, this is your minus 1. So we have 1. Then here we will have 1, then minus 3. So we have minus 2, minus 1. So minus 3. So this is your 1, then we have minus 3. So 1 minus 3, so minus 2, then minus 1, minus 3. Now this is your 2 and 0, then 1, 3. So this is your a square. Then a cube will be a square into a. So this is equal to minus 4, minus 1, minus 2, minus 6, 11, 4, 1, minus 3, 3. Then your a is 0, 1, 2, 2 minus 3, 0, 1, 1 minus 1. Now this is equal to, this is your plus. Now first row into first column will give you 4 is 0. So we have minus 2, minus 2. So this is your minus 4. The first row into first column will be 0. Then we have minus 2, minus 2. So this is your minus 4. Then we have 4 plus 3. So we have 7, 4 plus 3. So 7 minus 2. So this is your 5. Then we have 8 plus 2. So this is your 10. Then we have minus 0. Then 22 plus 4. So this is your 25. Second row into first column is equal to 22 plus 4, 25. Then we have minus 6, minus 33. So minus 39 plus 4. So we have minus 35. Then we have minus 12, minus 4. So this is your minus 16. Then here we will have the third row as minus 6 plus 3. So we have minus 3. Then the second element will be your 1 plus 9. So this will be your 10 plus 3. So that is 13. Then we have 2 and minus 3. So this is your minus 1. So if we check this element, then this is equal to minus 4, 5, 10. We have 25. So minus 35, minus 16, minus 3, 13 and minus 1. This element is your 26. Then let me check this element. So this is your 22 plus 4. So this is your 26. Now we have to prove that this is equal to 0. So let us take the left hand side. So left hand side, a cube plus 4a square minus a minus 12 is equal to your a cube is minus 4, 5, 10. Then we have 26 minus 35 minus 16 minus 3, 13 minus 1 plus 4 a square. We have 4 minus 1 minus 2 minus 6, 11, 4, 1 minus 3, 3. Then we have minus a means your 0, 1, 2, 2 minus 3, 0, 1, 1 minus 1. Then we have minus 12 and I means identity matrix. Now here this is equal to, so the first element is minus 4, then we have plus 16, so this is your minus 12, plus 12, and again here we have minus 12, so the first element is 0. Then let us check the second element. This is your 5, then here we have minus 4, so this will be your plus 1, here we have minus 1, then it is again 0. Third element, this is your 10, Now this is your minus 8, so this will be a plus 2, and here we have minus 2, so again it is 0. Then 26 minus 24, so we have plus 2 and minus 2, it is 0. Then we have minus 35 plus 44, so plus 44 plus 3, so we have 47, and here we have minus 12 minus 35, so it is again minus 47. So I think all the elements are equal to 0. So this is equal to 0. So that means our matrix A satisfies this equation number 1. So every matrix satisfies its characteristic equation. Now let us evaluate the second part, which is your a power 6 plus 4a cube minus a4 plus a square plus 4a square minus a plus 12. And before that, let us compute the inverse of the matrix. Now, because we have this condition a cube plus 4a square minus a minus 12i equal to 0. So let us multiply this equation by a inverse. So we have a square plus 4a minus I minus 12 a inverse equal to 0. So your a inverse will be equal to 1 by 12 of a square plus 4a minus I. So this is equal to 1 by 12. Then a square. Your a square is this one. Your a square is 4 minus 1 minus 2 minus 6 11 4. Then we have 1 minus 3 plus 3. Then we have 4 times a. Your a is 0 1 2 2 minus 3 0 1 1 minus 1. Then identity matrix 1 0 0 0 1 0 0 0 1. So this is equal to 1 by 12. Then 4 minus 1, that is your 3. Then we have minus 1 plus 4. So this is your plus 3. Then we have minus 2 plus 8. So 6. Then we have minus 6 plus 8. So this is your 2. Then we have 11 minus 12. So 11 minus 12 will be minus 1 minus 1. This is your minus 2. Then we have 4 here. So this element will be your 1 plus 4. So 5. Then we have minus 3 plus 4. So this is your plus 1. Then we have plus 3 minus 4. So this is your minus 1 minus 1 minus 2. So the A inverse of the matrix is equal to 1 by 12, 3 3 6. Then we have 2 minus 2 4. Then we have 5 1 minus 2. So this is the inverse of the matrix. Now let us find out the value of this expression. Now let us assume that this equation is equation number 2. Now the value of a6 plus 4a power 5 minus a power 4 plus a cube plus 4a square minus a plus 12. Now this can be written as, let us take a cube from here. So if you take a cube, then this will be your a cube plus 4a square minus a. Now then we have again a cube plus 4a square minus a plus 12i plus 12i. Now again the value of this bracket is equal to 12i with the help of the equation number 2. So from 2, the value of a cube plus 4a square minus a is equal to 12i. So this is your a cube into 12i. Then again the value of a cube plus 4a square minus a is again your 12i. So this will be your 12i plus 12i. So by 1, by equation 2. So we have 12a cube plus 24i. Now the value of, we have the value of a cube as this one. So this is equal to 12 prime a cube. So your a cube is minus 4, 5, 10. Then 26 minus 35 minus 16 minus 3 13 minus 1. Then we have 24 into I. I is your identity matrix. Now you can easily simplify this one to get the value of this expression. So here, with the help of the Cayley-Hamilton theorem, we have the value of such complex matrix, and again we have evaluated the inverse of the matrix with the help of the Cayley-Hamilton theorem. Satisfy its characteristic equation, and our matrix is, we have the matrix as 2 1 2 minus 1 1, then we have minus 1 2 minus 1, then the third row is 1 minus 1 2. So that this matrix satisfies its characteristic equation and find A inverse. So solution, your characteristic equation is determine A minus lambda I equal to 0. So this will give you. Now let us subtract lambda from the diagonals. So we have 2 minus lambda, minus 1 1, minus 1 2 minus lambda, minus 1. Then we have 1 minus 1 2 minus lambda equal to 0. So this is equal to now this is equal to 2 minus lambda, then this is your 2 minus lambda whole square plus 1, then we have minus 1 minus minus plus, so this is your minus 2 plus lambda, then we have minus minus plus 1, then again we have 1, so this is your plus 1, then we have minus 2 plus lambda, and this is equal to 0. Now we have 2 minus lambda plus lambda square minus 4 lambda plus 4 plus 1, so this is your 5. Then we have lambda minus 1, then we have lambda minus 1 again, this is equal to 0. So from here we have minus lambda cube, then we have plus 4 lambda square plus 2 lambda square, so we have 6 lambda square, then we have minus 8 lambda and minus 5 lambda, so minus 30 lambda plus 10 plus 2 lambda minus 2 equal to 0. So from here we have lambda cube minus 6 lambda square. Now this is your minus 13 plus 2, so this is your minus 11, so we have plus 11 lambda. 10 plus 2, 10 minus 2 is 8, so we have minus 8 equal to 0. This is your minus minus plus, so we have minus 8. So this will be your 4 minus 1, so we have 3. Now again, here we will have a mistake. So this is your minus lambda cube, then minus 6 lambda square, then we have minus 13 lambda, so this is your plus 6. So we have minus lambda cube minus 4 lambda plus 4 lambda square, so 6 lambda square, then we have minus 3 lambda minus 8 lambda, so this is your 11 lambda. Now minus 11 plus 2, so this is your minus 9, so we have plus 9, and this is your 6 minus 2, so this is your plus 4, so we have minus 4. So this is the value of this characteristic equation. Now as every matrix satisfies its characteristic equation, so we have to prove that. Now we show that a cube minus 6a square plus 9a minus 4 I is equal to 0. So to verify Cayley-Hamilton theorem, we will replace our lambda by a, and we will show that this right hand side is again 0 for a. So for that, let us compute a square. So your a square will be a into a. So we have 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2 multiplied by again. So this will come as, so this a square, I am not going in the calculation, so here I am directly writing the values of the rows. So this first row is 6 minus 5, 5. Then we have minus 5, 6, minus 5. Then the third row is 5, minus 5 and 6. So this is your first row, the value of a square. Then we have a cube as a square into a. So this is equal to 6 minus 5, 5, minus 5, 6, minus 5. Then we have 5, minus 5, 6, multiplied by a. Again your a is 2, minus 1, 1, minus 1, 2, minus 1. And then we have 1, minus 1, 2. So the value of a cube is equal to, now your a cube is equal to 22. Then we have minus 21. Then again we have 21, minus 21, 22, minus 21. Then the third row is 21, minus 21 and then 22. So we have the values of a square, a cube. Now to prove this equal to 0, so this is equation number 2 and this is your 1. Now let us take the left hand side of equation number 2. So the left hand side is a cube minus 6a square plus 9a minus 4i. So this is equal to a cube is 22 minus 21, 21. Then we have this row and the third row is this one. Then we have minus 6 into a square, 6 minus 5, 5 minus 5, 6 minus 5. Then we have minus 5, 5 minus 5 and 6. Then we have 9 times a, your age, 2 minus 1, 1, minus 1, 2 minus 1, 1 minus 1, 2. And the minus 4 times I. Okay. Now, this is equal to, so this is your minus 36 plus your 18, so plus 18 and plus 22, so this is your 40, and minus 36 minus 4 is again minus 40. So the first element is 0. Now the second element, this is your minus 21, here we have plus 30, then we have minus 9. So plus 30 minus 9 is your plus 21, so minus 21 is 0. Then again we have 21 minus 30 plus 9. So this is again 0. Then we have minus 21 plus 30. So plus 9 minus 9 again 0. Then we have 22 minus 36. So we have minus 14. Then we have plus 18. So plus 4 and here we have minus 4. So we can see that this is equal to, so this is equal to 0, 0, 0, 0, 0, 0 and then 0, 0, 0. So this is equal to 0. So we can say that your left hand side is equal to the right hand side. That means the matrix A satisfies its characteristic equation. So the Cayley-Hamilton theorem verified. So we have verified the Cayley-Hamilton theorem. Now let us find out the inverse of the matrix. So by equation 2, or if we multiply this equation 2 by A inverse, then we have A square minus 6A plus 9I minus 12 minus 4, A inverse equal to 0. So your A inverse will be equal to 1 by 4, then we have A cube minus 6A plus 9. And this is equal to 1 by 4, the value of A square. Your A square is this one, 6 minus 5, 5. Then we have minus 5, 6, minus 5. Then we have 5, minus 5 and 6. Then we have minus 6 times A. So your A is 2 minus 1, 1. Minus 1, 2 minus 1. And we have 1 minus 1, 2. Then 9 times I. So we have 1, 0, 0, 0, 1, 0, 0, 0, 1. Now if we simplify this one, then our answer is equal to 1 by 4. Then the elements are 3, 1, minus 1, 1, 3, minus 1, 3, 1. Then we have minus 1, 1 and 3. So this is the inverse of the matrix A. And this is your 6 minus 12. So we have minus 6 plus 9. So this is your 3. Then we have minus 5 plus 6. So plus 1. And then we have 5 minus 6. So we have minus 1. So this is the inverse of the matrix. Now I will diagonalize a matrix A. So we have the topic diagonalization. Let A is a matrix with distinct or with linearly independent eigenvectors, then there exists a non-singular matrix capital P such that your P inverse AP is the diagonal matrix. So if A has n linearly independent eigenvectors, if A is a matrix, if A is a square matrix of order n, then with linearly independent eigenvectors, then there exists a non-singular matrix P such that your P inverse AP is the diagonal matrix, where the diagonal of the matrix D are eigenvalues of A, where the diagonal of the matrix D are the eigenvalues of the matrix A. Now again, P inverse AP is equal to D, where my P is said to be, where P is known as model matrix. Your P is known as the model matrix. Now from here, our A will be equal to P into D into P inverse. So this is our A, and if you want to calculate A square, then this A square will be P into D into P inverse. Then we will have again P into D into P inverse. So you can see that this is identity. So this is equal to P D square P inverse. So in general, your A to the power n will be equal to P D power n P inverse. So diagonalization is very important to find out the higher power of a matrix. So if you want to calculate nth power of a matrix, then it is equal to the P into D to the power n, and D to the power n is just a powers of the diagonal, and then this P into D power n into P inverse. So we can have the higher power of a matrix. Now similar matrices, two matrices A and B are said to be similar if there exists a matrix or non-singular matrix P such that B equal to P inverse AP. So if there is a matrix P such that B equal to P inverse AP, then we will say that our B is similar to A. For example, here in this case, our A is similar to the diagonal matrix D. Okay, now let us discuss a question, and we will try to diagonalize the matrix A, and then we will try to find out the higher order of a matrix. So question: diagonalize the matrix A equal to 113, 151 and 311, and hence evaluate a power 4 and then evaluate the powers of fourth power of a. I have already solved this question in my previous lecture, and in that lecture I have given its eigenvalues and eigenvectors. So here again I am not solving this problem. I will just copy the eigenvalues and eigenvectors. So solution, your eigenvectors, your characteristic equation is determine a minus lambda I equal to 0. So from here we have 1 minus lambda, then 1 3 1 5 minus lambda 1 3 1 1 minus lambda equal to 0. This is your characteristic equation, and we have already the roots of this characteristic equation, and the roots of this equation or the solution or the values of the lambda from this equation was your minus 2, 3 and 6. So your eigenvalues was minus 2, 3 and 6. You can also obtain these values directly with the help of a formula. We have a formula because this is your formula, lambda cube minus trace of a into lambda square. Then we have the sum of the minus a11, a22, a33 into lambda. Then we have the determinant of a equal to 0. Now with the help of this equation we can easily get the characteristic equation, and now with the help of this characteristic equation we can get the roots of this equation. So if you want to calculate, if you want to obtain characteristic equation directly, then this is your formula, which is your lambda cube minus trace. Trace means sum of the diagonals. So this is your 5 plus 1 plus 1. So this is your 7. So we have lambda cube minus 7 lambda square. Now what is your a11? A11 means this minor 5 into 1, 5 minus 1. So this will be your a11 will be your 4. Then we will have a22. Forget this row and this column. So we will have 1 minus 9. So this will be your minus 8. So your a33 will be 5 minus 1. So this will be 4. So we have 4 plus 4, 8 minus 8, so 0. So this is your 0. So this a11 plus a22 plus a33 is 0. Then determinant of a. Your determinant of a will be 1, 5 minus 1, so we have 4. Then we will have minus 1. Then this will be 1 minus 3. So 1 minus 3 means minus 2. Then we will have 3. Then 1 minus 15. So this is 1 minus 15. So we have minus 4 plus 2. Then we have minus 14. So this is your minus 42. So we have minus 36. So your characteristic equation will be lambda cube minus trace. Trace is your 7. So we have 7 lambda square minus determinant is minus 36. So we have plus 36 equal to 0. Now if you want to cross check whether lambda equal to minus 2 is a root or not, then put lambda equal to minus 2 here. So this will be your minus 8, and this will be your, if you put lambda equal to minus 2, then this will be your 28 plus 36. So you can see that this is your 0. So that means lambda equal to minus 2, 3 and 6 are the roots. And if you put lambda equal to 3, then this will be your 27. Now this will be your, if you put lambda equal to 3, then this will be your 63. Then we have 36. Now again you can see that this will be your 63. So this is again 0. If you put lambda equal to 6, again this will be equal to 0. So you can obtain directly, you can obtain the characteristic equation directly with the help of this formula, which is your lambda cube minus trace of a into lambda square plus the minus a11 plus a22 plus a3 into lambda, then minus determinant of a equal to 0. So with the help of this we can have the roots of the characteristic equation. Now in this case, our roots of the characteristic equation are minus 2, 3 and 6. Now I have already given you the eigenvectors for these three eigenvalues, and the eigenvectors was, now eigenvectors for minus lambda equal to minus 2, 3 and 6 are, I have already given you the eigenvalues in my previous lecture. This was your minus 1, 0, 1. This was your 1, minus 1, 1. Now the third was 1, 2, 1. So these three were the eigenvectors for these eigenvalues. So your model matrix is equal to the column of the eigenvectors. So the column of the eigenvectors will be minus 1, 0, 1. Then we will have 1, minus 1, 1. Now 1, 2, 1. So this is your P. Now let us find out the inverse of the matrix P, because we have to calculate D, and D is your P inverse AP. So for that we will need our P inverse. So determinant of P is equal to, so determinant means minus 1, then we will have minus 1, minus 2, so this is your minus 3, then we will have again minus 1, so this is your 0, then we will have minus 2, and then we will have 1, then this is your 0, then this is your plus 1, so it is equal to plus 3, plus 2, 5, so this is your 4. So determinant of P is 4. Now let us calculate the adjoint of P. So for that, adjoint of P will be the transpose of the cofactor matrix. Now let us find out the cofactors. So for this minus 1 we will have minus 1 and then minus 2. So this will be your minus 3. Now for this one we will have, forget this column and this row. So we will have 1, 0, minus 2. So plus minus 2 we have plus 2. Then the third, for this element we will have 1, minus plus, sorry, this will be a plus 1. Now for this element, forget this row and this column, so we have 0. Then for this element, forget this column and this row, we have minus 1, so this will be a minus, forget this column and this row, so we have minus 1, so this will be a minus 2, plus minus plus, so this is your minus 2. Now this column and this row will give you minus 1 and minus 1. So again we have minus 2, so this will be a plus 2. And for this row and this column we have 2 plus 1, so this is your 3. So this is your plus, minus and plus. So this is your 3. Then we have this, forget this column and this row, so we have minus 2. So this will be a plus 2, and then the third element, last element will be plus 1. So let me cross check it. So this is your minus 3, 2, 1, 0, minus 2, plus 2, 3, plus 2, 1. So the transpose will be minus 3, 2, 1, 0, minus 2, 2, 3, 2, 1. So this is your adjoint. Therefore your P inverse will be adjoint P upon determinant of P, and this is equal to 1 by 4, minus 3, 0, 3, 2, minus 2, 2, 1, 2, 1. So we have the values of, value of P inverse. Now let us calculate P inverse into AP. So P inverse into AP is equal to, this is your P inverse, 1 by 4, minus 3, 0, 3, 2, minus 2, 2, 1, 2, 1. This is your P, and then we have A, your age, 1, 1, 3. Then we have 1, 5, 1. And then the third row is 3, 1, 1. And then your P is equal to, your matrix P is minus 1, 1, 1, 0, minus 1, 2, then 1, 1, 1. Now this is your P inverse AP. Now this P inverse AP will be equal to your D. D means the diagonal matrix whose diagonals will be the eigenvalues. So this will be equal to the first eigenvalue. The first eigenvalue was minus 2, then 0, 0, then we will have 3, and then the last element will be 6. Now this will be equal to this one. Now let us cross check it whether it is equal to this matrix or not. It is equal to this diagonal matrix because our eigenvectors are linearly independent. You can prove that these three eigenvectors are linearly independent. If these three eigenvectors are not linearly independent, then this will not be equal to the diagonal matrix. It may be the triangular matrix. Here your determinant is equal to 3 plus 2 plus 1. We have 6. Now this has to be equal to the diagonal matrix whose diagonals are the eigenvalues of the matrix. So this will be basically equal to minus 2, 0, 0, 0, 3, 0, and then we will have 0, 0, 6. And it can be easily proved. Just multiply this is your 1 by 6, we have minus 3, 0, 3, 2 minus 2, 2, 1, 2, 1. Then if you multiply these two matrices, then we will have row into column. So this row into this column, we will have minus 1 plus 3, so this will be 2. Then this row into this first row into the second column, we have 1 minus 1, so this will be 3. Then the row into column, we will have 1 plus 2 plus 3 is 6. So we have row into column, so this is your 0. Then row into column, so we have 1 minus 5, so this is minus 4 plus 1, so 3. Then your row into the third column, so we have 1, 5, 1 plus 5 to the 10, 11, 12. Then the third row into first column, so this is your minus 3 plus 1, so we have minus 2. And then row into column, so we have 3 minus 1, so 2 plus 1, 3. So we have third row into column, so this is your 3 plus 2, 5 plus 1, 6. Now let us check our elements. So the row into column will give you minus 6, minus 6. So this will be your minus 12. Now if you divide by 6, so this will be your minus 2. So first element. Then we have minus 9 plus 9. So the second element is 0. Then we have minus 18 plus 18. The third element is 0. 2, 4. Then we have minus 4. So 0. Then we have 6, minus 6, 0. Then we have plus 6. So this is your, the row into column will be your 6. And here we have 3. So this has to be minus 3. So this is your minus 3. The second row into column. So here you can see that if you multiply this row by this column, then we have 1 minus 5. So minus 4 plus 1 minus 3. So now you can see that this is your 18. So this will be 0. This will be a 3. And then here we will have 36. Check it. So this the element will be 6 plus 24. So 30 plus 6. So we have 6. Now it is equal to the diagonal matrix. So as our eigenvectors was linearly independent, that is why we are getting here the diagonal matrix whose diagonal are the eigenvalues. Now let us calculate a power 4. So your a power 4 is equal to, therefore your P inverse AP is equal to D, and your A will be equal to PD P inverse, and your A power 4 will be equal to P D power 4 P inverse, and this is equal to your P inverse is equal to, now your P is, the matrix P was this one, minus 1, 1, 1, 0, minus 1, 2, 1, 1, 1. Now D power 4 means it's power 4. So this will be your 2 power 4 will be 16, 0, 0. Then we will have 81. Then 6 power 4 will be 36 square. So this will be your equal to 1296. And then we have P inverse. For that we have written 1 by 6 here. And we have this one equal to minus 3, 0, 3, 2, minus 2, 2, and 1, 2, 1. Now, if you multiply these three matrices, then this will be equal to 2, 5, 1, 4, 8, 5, 2, 3, 5. Then we have 4, 8, 5, 1, 0, 5, 1, 4, 8, 5. So 2, 3, 5, and 4, 8, 5, 2, 5, 1. So this is the value of a power 4 with the help of this diagonal matrix, and we can also have the higher values of the higher power of the matrix.